Bismillahirrahmanirrahim. So today's topic is frequent pattern FP growth algorithm in data mining. So first we will discuss some shortcomings of a priori algorithm that FP growth algorithm has overcome. So using a priori needs a generation of candidate item sets. As I hope you are already familiar that with each step a priori algorithm has to generate candidate item sets. So these item sets may be large in number if the item set in the database is huge. So if the items on the backend are huge, then these item sets may be very large. So scanning the database again and again multiple times to check the support of to check the frequency of occurrence of each item set has high cost. It consumes more time. So these shortcomings can be overcome using the FP growth algorithm. So frequent pattern growth algorithm is an improvement to the a priori method or algorithm. A frequent pattern is generated uh, without the need for candidate generation. As in a priori algorithm, we have to scan and generate candidate item set multiple times, but here there is no need to generate candidate item set again and again. FP growth algorithm represents the database in the form of a tree. Here, the database is represented in the form of a tree, which we call frequent pattern tree or FP tree. So what is FP tree? Frequent pattern tree is a tree-like structure that is made with the initial item sets of the database. So the purpose of it is to mine the most frequent pattern. Find the items that occurs most frequently in the data set. So uh, each node of the FP tree represents an item of the data set. The root node represents null. So if this is a root node, it will be null, while the lower nodes represents the item sets. The association of the nodes with the lower nodes, that is the item sets with the other item sets, are maintained while forming the tree. So let's understand all this with the help of an example. So this is transaction data having 5 transactions. These are the items. For example, in transaction 1, there are 1, 2, 3, 4, 5, 6 items. That is E, K, M, N, O, and Y. So we have to apply FP growth algorithm on this data. So the above given data is a data set of transactions with each letter representing an item. So now what we have to do, we have to write the items separately, and we have to count the frequency of occurrence of each item and write that in front of the item. Like A item occurs only once in the previous transactions, C item occurs only twice in the previous transactions, and in this way we make the table. Now we will take some minimum support threshold value that is, for example, 3. So now we have to take only those items whose support is equal or greater than 3. So a frequent pattern set is built which will contain all the elements whose frequency is greater than or equal to the minimum support, and minimum support is given as 3. So these elements are stored in descending order. of the respective frequency. After insertion of the relevant items, the set looks like this. Now the items with frequency lower than 3 will be removed, and the remaining items are sorted in descending order and mentioned in over here, like K5, E4, M3, O3 and Y3. Now for each transaction, now these are our transactional data. These are the items, original items in each transaction. So now for each transaction, we have to make ordered item list. How we make the ordered item list? It is done by iterating the frequent pattern set that we have generated in the previous slide, in which in front of every item the frequency is mentioned, and checking if the current item is contained in the transaction or not. Like the first item, now in the previous list, the first item in which was sorted in descending order is K. So we have to search in these items either K is present or not. So we have to maintain the order same as given in the frequent pattern set. So K is present in these items, so we will mention K. After that, in the frequent pattern set, E comes. So E is present over here. So we will follow the order as mentioned in the previous slide. So E, K, E, then M is present over here. So M, then O is present over here. So O, and then Y is present over here. So we will mention Y. Now again, we will follow the same order that is sorted in descending order. So K is present over here, so we write K. Then E is present over here, so we will write E. And in the same way, we have maintained ordered item list. So now all the ordered item sets are inserted in the tree data structure. Now we have to insert these ordered item set into the tree data structure. So first our first item is KEMOY. So root node will be null, as I told earlier. Then comes the turn of K. So in front we will mention the frequency or the support of that item. If another set comes with K in it, we will increase its frequency by 1. So K, E, another node in which we mention E, then another node M, O, and Y. So these are inserted with support count for each item as 1. Next is insert the key K, E, O, Y. So now K and E support we will increase by 1, as these two items are already in sequence in the tree. Then O is not directly attached with E, so we have to directly attach O with E. So we will make a new node in which we mention O and write its frequency as 1 or support as 1, and we will associate it with previous O. In the same way, we will make a new node which is attached with the O and mention its support as 1, and we will associate it with this Y. Next is to insert the set KEM. So again, KE are already in sequence in the tree. KEM all are already in sequence in the tree, so we will just increment its support or frequency by 1. Next is to insert the set KMY. So K is already there in the tree. After that, we want M in sequence. So we will make a new node M and mention it support as 1 and associate it with this N. And in the same way, next is Y. So Y is not directly attached with M. So we will make a new node for Y and attach it directly with M and mention its frequency as 1 and associate it with the previous Y. So inserting the set KEO. So now K is already first in the tree. So we will increase its support by 1, and the next to K is E. We will increase its support by 1, and O is already after E in sequence in the tree. So we will associate, it is already associated also. So we will just increase its support by 1. So in this way, the tree is constructed. Next is now for each item, these are the original items whose support is greater than 3, greater than equal to 3. The conditional pattern base is computed, which is the path labels of all the paths which lead to any node. Now, we have to basically mention the path over here that leads to item Y. We have to mention the path over here that leads to item O. If there are multiple paths, we have to mention them with their support value. So to Y, there are 3 paths. That is KEMO with support Y1, KEO with support 1, and KM with support 1, as you can see in the previous slide. And with item E, to reach item E, there is only means one path, that is K, whose support is 4. So note that the items in the below table are arranged in the ascending order of their frequencies. So now the items in the previous, these items are arranged in descending order. Now these are arranged in ascending order. So now for each item in the conditional frequent pattern, now for each item, the conditional frequent pattern tree is built. And how this tree is built? We have to basically, for each item in the conditional pattern base, we have to take the common items from one row and mention it with their support summed up. Fine. Like what is common in these 3 conditional pattern base? So only K is common over here. Like M is not here, so we will not. And so M is not common. So K is common, and the support count is 1, 2, 3. So 3. And next is what is common? K is common with support 3, and next is K is common with support 3, and next is K only, and support is 4. So next, from the conditional frequent pattern tree generated in the previous slide, the frequent pattern rules are generated. By pairing the items of the conditional frequent pattern tree set to the corresponding item as given in the below table. Like in the previous slide, uh, in the conditional frequent pattern tree, K is common. So we will make a pair of K with Y, fine, to generate frequent pattern rules. So K is paired with Y, fine, and frequent pattern rules are generated. So KY with support 3. Next is KE. So KE is paired with O to generate frequent pattern rules. So KO in the same way EO and then KE or EKO is with support 3. In the same way, rest are also generated. So now for each row in the previous slide, we two types of association rules can be inferred. Like for KY, like for first was KY with support 3. So two rules are generated. K implies Y or Y implies K. They can be inferred. Next, to determine the valid rule amongst the various rules generated from the previous slide, the confidence of each rule is calculated. And the formula for confidence, to check confidence is support, means if you want to check the confidence of ky, so support k union y, that how many transactions contains k and y both, divided by support of k, that how many transactions contains k only. So if the confidence value is greater than a certain threshold that is mentioned, minimum confidence value, so we will call that rule a valid rule. So the confidence of both the rules is calculated, and the one with the confidence greater than or equal to the minimum confidence value is retained. So advantages of FP growth algorithm, these we have discussed in the first slide also. So faster than a priori, it has no candidate generation in each, so that's why it has to scan the data set only 2 times. So disadvantages can be FP tree, as it has to be fit in memory. So it may be large for the large data set and may not fit in memory sometimes, and it is sometimes expensive to build. Thank you.